the relationship between a grounded center tap and noise reduction, when compared to a simple hot and neutral wire configuration, isn't explicitly defined within the given information. However, we can discuss the general principles of grounding and how they relate to noise mitigation in electrical systems. A grounded center tap system, often found in single-phase 3-wire systems, utilizes a transformer with a center tap that is connected to ground. This creates two voltage legs, typically 120 volts each, with a 240 volt potential between the two ungrounded conductors. The grounded neutral provides a return path for current and serves as a reference point for voltage stabilization. In contrast, a simple hot and neutral wire system, typically a 2-wire circuit, consists of one ungrounded conductor carrying the current and a neutral conductor serving as the return path, which is also connected to ground at the service entrance. The effectiveness of a grounding system in reducing noise hinges on several factors, including impedance, bonding, and the type of noise present. Noise in electrical systems can manifest in various forms, such as electromagnetic interference, radio frequency interference, and common mode noise. Common mode noise is particularly relevant when discussing grounding systems, as it refers to noise signals that are present on both the hot and neutral conductors with respect to ground. A well-designed grounding system aims to minimize the impedance between the neutral conductor and ground, providing a low impedance path for noise currents to flow back to the source. This helps to reduce the voltage difference between the neutral and ground, thereby minimizing noise voltage across sensitive equipment. The grounded center tap, by its very nature, creates a balanced system with a grounded neutral. This balance can help to reduce common mode noise by providing a stable reference point for both voltage legs. The lower impedance ground path associated with the grounded center tap, when properly implemented, can offer improved noise reduction compared to a system with a less robust grounding arrangement. However, it's crucial to acknowledge that the specific noise reduction capabilities depend on the overall system design, the quality of the grounding connections, and the characteristics of the noise itself. Firstly, impedance plays a vital role. A lower impedance ground path allows noise currents to flow more easily to ground, reducing the voltage drop caused by the noise. Secondly, proper bonding is essential. Bonding refers to the interconnection of all metallic parts of the electrical system to create a continuous ground path. This minimizes voltage differences between different parts of the system and reduces the risk of electric shock. Thirdly, the type of noise is a factor. Different types of noise require different mitigation techniques. For example, shielding can be effective in reducing electromagnetic interference, while filters can be used to block radio frequency interference. The National Electrical Code, or NEC, provides guidelines for proper grounding and bonding of electrical systems. These guidelines are designed to ensure safety and minimize noise. Section 250 of the NEC covers grounding and bonding requirements. It specifies the size of grounding conductors, the methods for connecting to ground, and the requirements for bonding different parts of the electrical system. The NEC also addresses the issue of objectionable current. Objectionable current is current that flows on grounding conductors. This current can cause noise and interfere with the operation of sensitive equipment. The NEC provides rules for minimizing objectionable current, such as ensuring that the neutral conductor is properly isolated from ground except at the service entrance. To delve further into the specifics, consider the following aspects of grounding systems and noise reduction. Firstly, single-point grounding is a technique where all grounding connections are made to a single point. This helps to minimize ground loops, which can be a source of noise. Secondly, isolated grounding is a technique where the grounding conductor for sensitive equipment is isolated from the normal equipment grounding conductor. This can help to reduce noise caused by ground currents. Thirdly, the use of surge protective devices, or SPDs, can help to protect equipment from voltage surges, which can also be a source of noise. SPD divert surge currents to ground, preventing them from damaging sensitive equipment. To understand the practical implications, let's consider a few examples. In a hospital setting, sensitive medical equipment requires a clean and stable power supply. A properly designed grounding system with a grounded center tap can help to minimize noise and ensure the reliable operation of this equipment. In a data center, servers and other IT equipment are also sensitive to noise. A well-designed grounding system can help to prevent data corruption and system crashes. In an industrial facility, motor drives and other heavy equipment can generate significant amounts of noise. A robust grounding system can help to minimize the impact of this noise on other equipment in the facility. The size of the grounding conductor is also an important consideration. The NEC specifies the minimum size of the grounding conductor based on the size of the ungrounded conductors. A larger grounding conductor provides a lower impedance path for noise currents to flow to ground. The material of the grounding conductor is also important. Copper is the most common material used for grounding conductors because it has a low resistance and is resistant to corrosion. The connections to the grounding electrode are also critical. The connections must be tight and corrosion resistant to ensure a low impedance path to ground. Grounding electrodes can take various forms such as ground rods, ground plates, and underground metallic water pipes. The NEC specifies the requirements for grounding electrodes. In addition to the NEC, other standards organizations, such as the Institute of Electrical and Electronics Engineers, or IEE, provide guidance on grounding and noise reduction. The IEE STD 142, also known as the Green Book, provides recommended practices for grounding and bonding of electrical systems. To summarize, while the original prompt lacks specific details about how a grounded center tap reduces noise compared to a hot and neutral wire, we can infer that a properly implemented grounded center tap system with its balanced configuration and low impedance ground path can offer improved noise reduction capabilities. This is due to its ability to minimize common mode noise and provide a stable reference point for voltage. However, the overall effectiveness depends on several factors, including the quality of the grounding connections, the type of noise present, and the overall system design. It is also important to follow the guidelines of the NEC and other relevant standards to ensure that the grounding system is properly installed and maintained. Consider the impact of grounding on sensitive electronic equipment. These devices often contain microprocessors and other components that are highly susceptible to noise. Noise can cause these devices to malfunction or even fail. A properly designed grounding system can help to protect sensitive electronic equipment from noise and ensure its reliable operation. Also, ground loops can be a significant source of noise in electrical systems. A ground loop occurs when there are multiple paths to ground. This can create circulating currents that generate noise. Single-point grounding is a technique that can be used to minimize ground loops. In addition to grounding, shielding can also be an effective way to reduce noise. Shielding involves enclosing sensitive equipment in a conductive enclosure that is connected to ground. This helps to block electromagnetic interference and radio frequency interference. Filters can also be used to reduce noise. Filters are circuits that are designed to block certain frequencies of noise. Filters can be installed at the input of sensitive equipment to prevent noise from entering the equipment. The use of isolated grounding can also be beneficial in some cases. Isolated grounding involves isolating the grounding conductor for sensitive equipment from the normal equipment grounding conductor. This can help to reduce noise caused by ground currents. It's crucial to understand the interplay between grounding, bonding, and shielding to achieve optimal noise reduction in any electrical system. Firstly, grounding provides a low impedance path for fault currents to flow back to the source, protecting personnel from electric shock. Secondly, bonding ensures that all metallic parts of the electrical system are at the same potential, minimizing the risk of electric shock and reducing noise. Thirdly, shielding blocks electromagnetic interference and radio frequency interference, preventing them from affecting sensitive equipment. When designing a grounding system, it's important to consider the specific needs of the application. For example, a hospital requires a more robust grounding system than a typical office building. The hospital's grounding system must be designed to protect sensitive medical equipment from noise and ensure the safety of patients. In addition to the technical aspects of grounding, It's also important to consider the regulatory requirements. The NEC and other codes and standards specify the requirements for grounding and bonding of electrical systems. It's important to comply with these requirements to ensure the safety and reliability of the electrical system. The type of electrical system also influences the grounding requirements. For example, a separately derived system, such as a generator, requires its own grounding electrode system. The grounding electrode system for a separately derived system must be installed in accordance with the NEC. The location of the grounding electrode is also important. The grounding electrode should be located as close as possible to the service entrance or the separately derived system. This minimizes the impedance of the grounding conductor and improves the effectiveness of the grounding system. The maintenance of the grounding system is also crucial. The grounding connections should be inspected regularly to ensure that they are tight and corrosion resistant. Any damaged or corroded grounding conductors or connections should be replaced immediately. Proper grounding and bonding are essential for ensuring the safety and reliability of electrical systems. A well-designed grounding system can protect personnel from electric shock, minimize noise, and prevent equipment damage. It's important to follow the guidelines of the NEC and other relevant standards to ensure that the grounding system is properly installed and maintained. The effectiveness of a grounded center tap in reducing noise is also influenced by the load balancing on the two voltage legs. Ideally, the load should be evenly distributed between the two legs to minimize neutral current. Excessive neutral current can contribute to noise and voltage drop. The use of harmonic filters can also be beneficial in reducing noise in electrical systems. Harmonic filters are designed to block harmonic currents, which can be a significant source of noise. Harmonic currents are generated by nonlinear loads, such as electronic ballasts and variable frequency drives. The implementation of proper grounding techniques is an ongoing process that requires careful attention to detail and a thorough understanding of electrical principles. By following the guidelines of the NEC and other relevant standards, and by paying attention to the specific needs of the application, it is possible to design and maintain a grounding system that is both safe and effective in reducing noise. Firstly, understanding the different types of grounding systems, such as solidly grounded, impedance grounded, and ungrounded systems, is crucial. Secondly, knowing how to properly size grounding conductors and select appropriate grounding electrodes is essential. Thirdly, being able to identify and mitigate ground loops is a valuable skill. Finally, keeping up to date with the latest changes to the NEC and other relevant standards is important for ensuring compliance and best practices.